Thanks for coming here. Today, I will present our paper, Scheduling Deep Learning, Real-Time Deep Learning Services as Imprecise Computations. Let's just get started. With the recent advance of neural network technique, deep learning services become some indispensable component in autonomous real-time system. For example, if you check the state-of-art autonomous vehicle architecture, you can always see some this architecture include deep learning services that are used to detect the objects, lands, and humans based on the camera and the later sensing input. But the challenge we encounter, the problem is that the current deep learning services still lack the support from the real-time scheduling. For example, for autonomous systems such as autonomous vehicle or drone, these platforms typically have a multiple sensor. You will see here, they have multiple cameras and multiple lidars. So if each of them, so a lot of time each of these sensors needs a deep learning services that are used for high-level machine perceptions as well as semantic understanding task. So all these computations, all the computation become a huge burden for the local computation for our local computation devices. And on the other hand, in order to make the deep learning services more compatible with real-time scheduling algorithm, so ideally, I would say each deep learning workflow should better support the dynamic inference complexity, difference utilities, data law, and the criticality assessments as well. So therefore, we can see that the current deep learning services naturally calls for refactorization of neural network pipeline that can better support the real-time scheduling. So with such an idea in our mind, the motivations of this paper is actually to somehow to try refactoring the neural networks for real-time scheduling. And the preliminary answer we have made in this paper is that we can actually cast the deep learning workflow as imprecise computation task. So the connection between the imprecise computation and deep neural network is actually straightforward. Since neural network usually has hundreds or tens of hundreds of layers, so we can easily separate the whole neural network into multiple stages, and then within each stage we have multiple layers. So an example is that we can just take the first stage as the mandatory part and the left several stage as the optional part, so that we can easily link the neural network with the idea of imprecise computations. We can easily see their connections. So in addition, we can also append a classifier at the end of each stage. So therefore, the confidence output of classification result of each stage can naturally serve as the utility of the optimal part. And we will see later, these utilities for optional parts are actually data dependent and they're very helpful for scheduling. So with this kind of formulation, the kind of first straightforward question we will ask is that, what's the advantage of such formulation? So we can summarize the advantage of a new formulation into two parts. The first advantage is that by refactoring deep learning as imprecise computations, we can enable data-dependent inference complexity. So we will see in a lot of cases. So the input data, the complexity are totally different. So for the figure on the top, we will see a lot of figure. We just have a very simple input. So actually, which means we don't have to spend a lot of resources, a lot of time to force their inference. So maybe for a very normal car, maybe only run the mandatory part is always enough to give us a high confidence classical result, which is correct. So however, there are also some part of other inputs, other image, other inputs that are very complicated to recognize very complicated to inference by nature. So the advantage of our design is that based our design of casting deep learning as imprecise computation, now the real-time system has the ability to identify the complexity based on the utility for each classify at the end of the each stage. And what's more, now so we are able to schedule more computation to these more complicated data input samples, so that in all, when we counting the overall utility, overall rewards, we can achieve a better overall utilities when we counting the multiple inputs which have a mixed complexity at the same time. On the other hand, we will say our design of deep learning as imprecise computations also enable the anytime predictions and inference preemption as well. So with the real times that take the deep learning services as a program, so it's very nature assumptions that we will take the mixed criticality input. So within such conditions, so treating deep learning as imprecise computations help us to better solve the priority inversion problem. So for example, so naturally a case will be at the beginning, the system just only receive a low priority input. So that naturally we just launched the corresponding deep learning inference. But the problem, the issue is that when we run our neural network into the middle of some layers, so we also we then received an high priority input. So if we are just using some traditional neural network model, that all the computation, all the complexity are predefined before the execution start, so we will encounter a problem. So we have to either abort the low priority workload, so which means we have we don't have any output, any prediction for this low priority input, or we have to continue the neural network inference for this low priority inputs, which means we will cause some priority inversion problem in our real-time system. Both of the choices are not good. So, but if we use our deep learning as imprecise computation model, we can have a third choice. That is, we can interrupt our, I would say, on the model level. So now we are able to interrupt our low priority inference, and we can at the same time we can still return a valid solution, a valid classification result, because once our neural network inference has passed the mandatory part, we already have some checkpoint for the temporal output. So that is the meaning of treating deep learning imprecise computation. That is, we can provide an anytime prediction. So anytime after the mandatory part, anytime we want to interrupt the neural network inference to avoid the priority inversion problem, we can do it, because we always can give you an output for the classification result from the latest stage inference with our formulations. So in summary, I would say in this paper, we mainly made two contributions. The first contribution is what I mentioned before, is that we in our paper, we refactor the deep learning neural network into imprecise computation workflow, which can be very a nice formulation to enable a lot of property we use in real-time scheduling. And also the second part of contribution is that we propose a real-time scheduling framework with such no formulation. Because if we only have the idea of refactoring neural network into imprecise computation, that is not enough. We still need to have several additional components to support the end-to-end real-time scheduling framework. The first component is that we need to train our multi-stage neural network with confidence calibrations. So kind of a problem we'll encounter is that if we just we just train our multi-stage neural network with a normal method, we'll encounter problems that the output confidence for our classify is not equivalent to the empirical accuracy, which means we can have a very low confidence output, but turns out the accuracy is much higher. So to give a long story short, so the problem itself is a very important research problem. Just make a long story short, we just take the technique from our previous paper, reliable deep sense. So basically, if we train the neural network based on the technique mentioned in this paper, we can provide for each classification result, can provide a well-calibrated confidence estimations, and this confidence is almost equivalent to the expected accuracy empirically. So that means we can take the classical result with a faithful estimation of our deep learning services utilities. But if we only have a calibrated confidence estimation, is not enough, because for real time, we always need to estimate the utility of future state we have never execute. So we also need to have some dynamic utility curve estimation module. And in this paper, we have proposed several heuristic, and we empirically evaluate this heuristic with a real data set in our experiment. And the last component is that we need to assign the depths for each neural net task. We need to schedule the stage in the neural network services with a scheduler. The major target of our scheduler is that we want to decide the number of stage for each neural network task to run, so that we can maximize the overall reward. And in this paper, overall reward means the overall confidence that is achieved by all the neural network inference tasks. And in this paper, we also have an assumption that in our stage scheduling algorithm, we always take the earliest deadline first as an underlying scheduling policy. So in this paper, we solved the stage scheduling algorithm with actually a very simple dynamic programming formulations. And we ensured we don't have a very large runtime overhead by a fully polynomial time approximation scheme. So basically, design pretty simple. We just made two tricks. The first is that we uniformly quantize our rewards based on a constant step delta. So which means now the reward, the confidence is not continuous, it is quantized. And we can easily bound the number of quantization element since the maximum number of confidence is upper bound by 1. So if we have totally n tasks, at most we will have only n total confidence rewards. And the second trick we made is that we since our underlying policy is earliest deadline first scheduling algorithm, we maintain and priority queues that we are indexing our deep learning task according to their absolute deadline, which means J1 means the task with the least, the earliest the absolute deadline, and the JN means the task with the last absolute deadline. And then we, as you see on slide, we can maintain the table. The columns of table are quantized the rewards, and the row of table is the tasks. So the entry in the table PIR means that entry records the least amount of execution time used by the top I tasks achieve exactly R total reward. So then based on the formulation of dynamic programming, so we as you may know, we can very easily filling out the whole table with a simple recursive relationship. And once we have that, we can trace back to achieve the optimal state scheduling and depth assignment. In addition, an interesting property of fully polynomial time approximation scheme is that we can also provide a kind of worst case performance bound. We have proven on papers that if we set our quantization step delta to be epsilon R over n, So we can make sure that our final solutions have at least 1 minus epsilon of the optimal solution. And then we see the evaluation. So in this paper, we basically evaluate the image recognition task with 2 data sets. One is CIFAR10, which have 10 classes, image classes. The other is ImageNet, which have 1,000 of classes. And in the experiment, we emulate K concurrent clients that generate services request, random service request. And within each time interval, each request comes with a relative deadline and a random image. And the relative deadline is drawn by a uniform distribution, which controlled by 2 parameters. One is upper bound of deadline, du, one is lower bound of deadline, dl. So the evaluation contains 2 parts. The first part is to evaluate the utility estimation, utility confidence prediction part. As we mentioned before, in this paper, we propose 3 types of heuristic for future stage utility predictions. The first heuristic is that we always assume the distance between the current utility to the optimal utility decreasing and exponential manner, which means the next stage will always reduce the distance to the maximal stage in half. And the second heuristic is that we always assume that the next stage will increase the utility to the maximum value 1. And the third heuristic is that we assume the next stage will continue to improve the utility in a linear fashion. And also we compare with the optimal utility curve prediction algorithm, which means in this algorithm, we know exactly the computed confidence after each stage beforehand. So here is the result from for both CIFAR10 and for the ImageNet dataset. So basically, we will see that the exponential heuristic always performs the best in the different cases. In terms of accuracy, you can always achieve the best performance. And it's very near to the optimal case where we already know all the confidence beforehand. The second part of evaluation is try to evaluate our stage scheduling, which are used for utility maximizations. So other than our real-time deep IoT framework proposed in the paper, we also have 3 baseline. The first baseline is simply earliest deadline first algorithm. The second deadline is called least confidence first. At each time, it picked the task with the least confidence to run the next stage. And if we encounter a case that 2 tasks have the same confidence, that the least confident first scheduler will pick the one with the earlier deadline. So it just implicitly take the deadline into consideration. And the last one is called round robin. So the scheduler will select a stage to run among all the tasks in a round robin fashion. But in each round, it will take orders that will take the task with the least execution stage as the first to run. So also we will see here is the evaluation result for the CIFAR10 datasets. The upper 3 figure, the y-axis is the accuracy, and for bottom 3 figure, the y-axis is the deadline missing rate. And for the x-axis, we are increasing the number of emulation concurrent thread from 10 to 30. And other 2, we are increasing or decreasing the upper bound and lower bound of the deadline for our emulated the request. You can see basically in all cases, our real-time deep IoT, RT deep IoT always perform the best. Which provide a pretty promising result, I would say. And also, last we will see the overhead. I have to admit the overhead is still a little bit large because we not fully optimize our code and do the pipeline very well. But even in that case, we have a user space scheduler. We can also always maintain the overhead around 5%. So in conclusion, in this paper, we have made two contributions. The first is that we will factor the deep learning framework into imprecise computation workflow, which support a lot of interesting property, like we can support anytime predictions, we can do the inference preemptions, and also support the data-dependent inference complexity to improve the overall scheduling, so maximize the utility. And on the other hand, we designed a real-time scheduling framework based on our new formulations, and we have designed all three components which are needed in the framework, and we do the evaluation to showing that our formulation is helpful and our frameworks have a promising result, and hope it can help us to think about how could we better reflect the deep learning framework for real-time scheduling in the future work. And thank you for your attention.